Good morning. So we were now in an important part of our vehicle dynamics course, learning lateral dynamics. And in the last class, we looked at importantly motion called the steady state motion of your vehicle and its fundamental governing equation derived. And then we have looked at the physical insights of a vehicle behavior based on an important coefficient called the understeer coefficient, which is primarily depends upon the values of normal loads present at the front and rear axle wheels as well as the tire cornering stiffness. So this is what in summary we were able to look at steady state motion and understeer coefficient, or otherwise called understeer gradient, and that was used to categorize the vehicle behavior during hard cornering at mid or high speed cornering. So what was that we were doing? We were able to define vehicle neutral steer effect, vehicle understeer effect, and vehicle oversteer effect. Looking at physical vehicle on a curved path, or the vehicle originally going in a straight line, if there is a side force acting on it, how are these tendencies are pronounced in the vehicle is what we have seen in the last class, and we have stopped there. I'm going to start from the point where we left in the last class to continue further to add on more and more understanding on steady state behavior of your vehicle and steady state motion of your vehicle, right? So let me share my screen for that alone. Hope you are able to see the screen, and this is lecture number 22, and today's date 4/10/2021. So what is that in today's class that you are going to look at is you're going to look at two important points. One is what is called handling diagram. And then we are going to look at there are various tests that are conducted with the steady state motion for predicting the handling behavior of vehicle. So there are various tests for handling behavior of vehicle. So this is what we are going to learn today's this one period, and I'm going to start for that today's class writing down fundamental governing equation for steady state motion. Fundamental governing equation of motion for steady state. So you know that is essentially given by one equation, that is the lateral force necessary to be developed would be given by MRU. So there's only one equation is what is governing equation for steady state motion, as yaw velocity or lateral velocity are independent of time. It's not varying. So only acceleration that's present in your vehicle is centripetal acceleration, and that is lateral acceleration, otherwise called, would be given by U squared by R, where this R is turning radius of your vehicle when you are going on the path, and U is forward velocity, which is constant here. It is considered. So this AY is equal to U squared by R is only what is there present as an acceleration, and that maintains the directional control or directional behavior of your vehicle, right? And we have derived this in another form in terms of bringing in the vehicle parameters through an important equation, that is the requirement of steering angle is given by L by R plus KUS into AY, KUS into AY by G, AY by G. So of course, we had got this as how L by R plus KUS, where this AY is what is U squared by R. So U squared by RG. So this is that equation number 6, which is the fundamental governing equation of steady state motion, where you define this KUS as understeer coefficient or understeer gradient it is called. So what is this understeer gradient primarily depends on? It is depends on WF by C alpha F minus WR by C alpha R. That's given by this, where the term WF by C alpha F or WR by C alpha are called tire compliance. In the front and rear axles respectively. So that is what I was telling, this understeer gradient, or in general the steady state motion of your vehicle depends primarily on the normal loads in the front axle and the tire cornering stiffnesses. And what is that assumption of our bicycle model which you have used to derive this governing equation are very important to look at this point of time. So one is what? The tire model is linear model. And number 2, no suspension is considered. The vehicle as a whole as one rigid body considered, right? There is no discretization of unsprung mass or sprung mass. We consider the entire vehicle as one vehicle, and we do not consider the effect of suspension in our model. And on the tire model is linear. That means what? We consider this C alpha F is equal to constant, or C alpha R is constant. How did we get that? Is from Fi variation of an individual tire as function of slip angle. The variation is limited by road adhesion coefficient. The slope drawn at alpha equals 0 is what is defining C alpha. So we have taken only this constant value. We do not consider the non-linearity. In reality, the tire cornering stiffness is non-linear behavior phenomena, and that we do not consider in our model. So these are the important assumptions with which we look at the bicycle model, and we have derived this governing equation from this equation Fi is equal to MRU from the free body diagram in the last class, and equation number 6, Roman letter 6, is what is the fundamental governing equation of steady state motion now. So this equation and its limitation, or it's an important assumption that you understand. Right, and we have plotted this essentially in the last class like this. What was that? We have taken a steering angle on y-axis and u squared by r on the horizontal axis. So when we have taken this, I think we were doing it in the last class like this. Could see that here. What we were doing. So we had this steering angle versus forward speed we were plotting. So when we have plotted that, you could see that that variation is parabolic here, and the variation is 0. It's constant for neutral state effect behavior of the vehicle. This is what is the negative slope you have for an oversteer vehicle. So this is what in the last class that we have looked at. So now, if I ask you to plot this with this, what is this U squared by RG? Now, this entire thing is what is AY by G, we can call, right? AY by G. So, if my forward speed is constant, R is constant, this AY is constant, right? But I would do some test where the speed I can vary every time. Then what will happen? I will have this AY. So what would be the steering angle requirement as function of lateral acceleration? If I ask you to plot, you would look at again this governing equation L by R plus AY by G into KUS into KUS. So KUS is 0 for neutral steer tendency of the neutral steer behaving vehicle. So at that time, it is only L by R of a 3-meter vehicle wheelbase and 30-meter radius. If I consider, I see that we have to have this. So what is the physical meaning? The steering angle required, irrespective of the variation of lateral axis, so lateral acceleration, you have the constant steering angle sufficient to negotiate the given radius. So in such case, the vehicle behavior is neutral steer behavior. So if I have to consider my KUS is positive, that means KUS is greater than 0 for understeered design vehicle, then the steering angle requirement as a function of lateral acceleration would be now varying linearly like this. Right? Linearly like this. Because we look at here now, if I differentiate this with respect to AY by G, this L by R happens to be constant and 0, and I have KUS, and that KUS is what is now here there. So what is that? D delta F by DAY by G, if I do with respect to lateral acceleration, if I differentiate. This part is constant 0, and I have KUS. If my KUS is positive, like in this case, what will happen as I increase my lateral acceleration, I will have this constant slope, and this is what is the variation that's going to be. On the other hand, if my KUS is negative, less than 0, for the vehicle which is designed for an oversteered vehicle, for example, the race cars are designed for oversteered tendency in order to negotiate the sharp turns and quick steering action, counter steer action that you could witness. You see that you would have the values negative. So that would go here like this. And there is a point where it intersects, where the steering angle requirement has become 0 at that particular lateral acceleration. And anything that beyond that lateral acceleration goes would have unstable state here. The unstable state of your vehicle or loss of steering control would be pronounced at this critical lateral acceleration. And the speed corresponding to that value is what is, we call it as critical speed of your vehicle, right? And so on. So this is what it would be. So if I have this graph, delta F as function of U, that's what in the last class you have seen here. Instead of a forward speed, if I consider delta F as function of lateral acceleration, I would have these. So here the slope is negative slope, right? If it is happens to be negative, then this is minus, so I will have this. So I could explain now the lateral handling behavior of the vehicle tendencies when that would be of neutral steered vehicle or understeered vehicle or for oversteered vehicle. And here we have this lateral critical acceleration corresponding critical speed, and beyond which if lateral acceleration increases, you do not have to you do not have a control of steering, because that time the steering angle is 0. That's something no very difficult to imagine. You want to negotiate a high speed, and your vehicle is oversteer vehicle, and this speed you are driving, and you don't require to give a steering angle. It turns, and it is going out of the control. That's what is that, and that's very dangerous. So as long as your lateral acceleration falls on this side, you have to have some steering angle requirement. So you give some steering input. If your AY by G is somewhere here below this, and that is the corresponding speed of the vehicle, even the vehicle is a oversteered design vehicle, it is under control. You would have to negotiate a curve. Instead of increasing the steering angle, you would decrease the steering angle. That's what you say counter steer, and that is normally can be witnessed by Formula One vehicle racer. They counter steer the vehicle in a sharp corner at high speeds. right? So this is what is that steady state behavior that we have understood. But in reality, in practical situation, do the vehicle behave in this fashion? That's a question mark. The vehicle which is originally designed for an understeer tendency can go into an oversteered tendency because of the operating condition of your vehicle, because of non-linearity of tire behavior, because of suspension that's to be accounted in your vehicle model. So if I have these assumptions, it's well good, and then this is what is that we have discussed. The moment I have to consider my tire is going to be a non-linear tire model, that means the C alpha F is no more constant, and it would be a function of slip angle here. I have to see this slope is varying here. In such cases, how do I account non-linearity of my tire behavior? If I account that, that is what is the real tire behavior. That's where the tire models were developed. We will study such tire models which could account non-linearity into your vehicle dynamics simulation separately in tire dynamics part of our course. For time being, we will consider this constant and we will proceed, right? And suspension is considered. What would happen if we have suspension? Then your mass is being discretized as unsprung mass and sprung mass, and there is a relative motion of sprung mass with respect to unsprung mass, and the relative motion would take place whenever you do a turn because of lateral load transfer from inside to outside, or whenever you are driving and you're steering and you are accelerating or braking, you would have a load transfer in longitudinal direction. Those load transfers all would come into picture the moment you consider suspension. If you do not consider the suspension, there is no load transfer accounted in this model, and this is what is the requirement of steering angle in this discussion, right? So what is that? The vehicle designed for understeer would always behave as understeer. The vehicle designed for oversteer would behave as this fashion, is what we conclude with these assumptions. But in reality, when you have to account the non-linearity and the suspension in account, how are these characteristics are explained is what you have to understand. For that reason, I am going to explain you now a diagram called handling diagram, right? Which is going to account these reality, right? So let's look at now what is handling diagram. Handling diagram. So the handling diagram to draw, let's again look at our fundamental governing equation, L by R plus KUS into AY by G. I'm looking at this again. I'm going to draw this diagram as taking on y-axis my lateral acceleration, AY by G on this axis. And on the horizontal axis, I'm going to take a parameter, horizontal axis. I'm going to take in this parameter that's coming from this. So I want to take this on y-axis. So I'll just to manipulate this like this. I will have this L by R taken on this side. So this KUS into AY by G is what is minus sign. If I take it out, L by R minus delta F would be on this side. So now, what is AY? It's U squared by R. So KUS U squared by R into G is what is minus L by R minus delta F. Minus of L by R minus delta F. And now, if I differentiate this with respect to this term, that is D A Y by G by D, this side, what is there is L by R minus delta F. If I do that, what is that I have with respect to this? So this is minus 1, and here it is KUS that is going on the side 1 by KUS. So this is what is now the differential. The variation of lateral acceleration is function of this quantity. So this quantity I can also rewrite it as like this. So I know small r into capital R is what is forward speed in my bicycle model, where small r is yaw velocity, turning radius. So r omega we say in rigid body mechanics, here rr is equal to forward speed. If that is so, I can change my equation as 1 by r curvature is going to be r by u, and if I put that over here, I can rewrite this as d a y by g, where it is normalized by this in terms of g's to say, and d into L by r is going to be r by uh, L by RL by U, RL by U minus delta F is what is minus 1 by KUS. So if I have this derivative, and if I look at now my variation of AY by G as function of this parameter, which parameter RL by U minus delta F. Delta F is what is given steering angle. RL by U is what is L by R, right? So with respect to that, if I plot, so what is on my horizontal axis? It is RL by U minus delta F. If I take it on this, so this variation is going to be for a real-time vehicle, something like this, where the vehicle is accounted with the real operating condition and tire nonlinearity, suspension, all are there. So I would be having this like this. So what is that? I take my vehicle and then I do the steady state motion in a test track, and I would be able to plot this plot. And this diagram is what is called handling diagram. And you see here I have a negative slope portion and positive slope portion, and also a point where the slope is infinity, correct? Infinity slope. So now what is that I going to infer from this? So when the slope is infinity corresponding to this value, the AY by G value refer to a neutral steer tendency of the vehicle. Neutral steer tendency of the vehicle. What is that? When this slope is infinity, that means minus 1 by KUS is infinity. So that means the KUS is 0 at that point of time, right? So this is corresponding to KUS equals 0. So that's referring to a neutral steer tendency. So on the other hand, down here it is understeer behavior. How? Look at now the slope here is negative slope, and that negative slope, if I substitute here, that's going to be positive KUS. So here in this KUS is positive, that is greater than 0. So this slope from this point till this point, it refers to the vehicle which is understeer tendency of the vehicle. And here you see the slope which is positive slope, but here there's a negative sign. So this would take care to state that this is here the behavior is oversteer behavior, because KUS is less than 0 value. So KUS is less than 0, KUS is greater than 0. Why? Because there's no more the KUS values constant, right? So when I consider here KUS value constant, you see here my diagram happens to be like that. In this, you could see, right? It's like that. Why? Because I have my KUS dictated by front tire compliance and rear tire compliance only, where C alpha is constant, C alpha is constant, and there is no suspension, so there's no lateral load transfer as long as I drive my vehicle with constant speed. So WF and WR also is constant. So if this happens to be greater than this, then I have KUS positive. On the other way, on the other hand, it is negative, that is reversed. So this is no more. So when this is non-linear and KUS would be varying. So how that is varying is what all can be looked at from various design aspects of your vehicle, operating condition of your vehicle, non-linearity of your tire behavior, the moment you account steering present in your model. There's something called roll steer effect, camber steer effect, or there are NVH aspects. There are bushes in the connections called compliance steers. These are all some additional transient effect that would be participating in your vehicle, and that would create the variation of KUS, and that is what has been captured here like that. So your variation can be plotted, and that can go like this, and when it goes like this, you would be able to define the vehicle behavior, right? So based on the lateral acceleration value, where are you accordingly you would be able to comment the vehicle handling behavior. So this is what is essentially a handling diagram called. This diagram is to say the behavior of road vehicle in lateral direction during high speed or moderate speed cornering for the varying operating conditions, right? Hope you followed this handling diagram. Now let's get into looking at what are the various tests that are conducted for handling characteristics. So testing of vehicle, testing of handling characteristics of vehicle, testing of handling characteristics of vehicle, So what are various tests that are conducted? So these tests are conducted on a test track called skid pad. Skid pad. What are these skid pad called? The skid pads are these skid pads are a flat surface, essentially a flat surface, and they are of asphalt road surface. And no, it's a smooth surface and it's a paved road. It is a paved road. So you can go to your test track and you see. So it's a smooth, flat surface is what is called a skid pad. So on that you have these tests are conducted. What are those tests? One is called the constant radius test. And then constant speed test. And third one is what is called a constant steer angle test. So we are going to look at these three tests in order to understand the handling characteristic of a vehicle. How are these tests conducted? So what are measured during this test? During this test, of course, the forward speed and the yaw velocity and the lateral accelerations are measured. If you see, sometime only yaw velocity would be measured, the lateral acceleration can be derived. Otherwise, lateral acceleration only measured and yaw velocity can be derived. So yaw velocity to measure, there is something called yaw gyro sensor is used. Yaw gyro sensors are used. And AY to measure, you have accelerometer. So this accelerometer can be at the CG location installed, and then you would be able to measure what is the lateral acceleration of your vehicle. And you know the relationship of AY is nothing but U squared by R. And if I know forward speed and I do a constant radius test, I know what is my lateral acceleration. So if I measure only forward speed in during constant radius test, I would know what is my AY, right? And sometime you have your R. So you know also this R into R is equal to U. So if I know forward speed, I can also get what is my R value. That's U by R, right? So these are all some kinematic relationship which already we have seen. And these relationships are used and to do. So what are these three tests? These three tests are conducted with steady state motion. These tests are steady state tests. Steady state test. So that's very important, right? So that means you are trying to see that the yaw velocity or the lateral velocity or forward speed all are not going to be varying as function of time invariant functions. So those steady state tests are conducted on a real vehicle with the constant radius test, constant speed test, and constant steer angle test. So let's look at one by one these tests, right? So constant radius test. constant radius test. Right, just 1 minute. I'll just come. Sorry, I'll get back to a lecture. This constant radius test, right? That's test number 1. So what are we going to do there? Is this. So your vehicle will enter into the test track, which is of constant radius test track. So your surface would be a circular path. So your vehicle would be driven along a circular path with a constant radius for various speeds. So what I'll do, I'll go with one particular speed and then complete. I'll go with the next speed and complete my test. I'll go with the third speed like that. So it is not I'm accelerating during my circular test. So I'm entering the track with the constant speed, maintaining. So there's only lateral acceleration would be present in mind. So for first speed, there will be one particular lateral acceleration, u squared by r. So when I have my second lap, I increase my speed, then there will be a lateral acceleration. Like that, I would increase my lateral acceleration as I sequentially increase my speed during this test. And then I would plot a graph from the measurements. So on this vertical axis, I'll take delta F, and that's going to be function of lateral acceleration here, right? So you can see again this equation would help you. Delta F is equal to L by R plus KUS into AY by G, right? So this is our fundamental governing equation for steady state motion. So if I differentiate d delta F by d AY by G, what is that I would be having? As this part is constant, I would have only KUS straight away. So this is very straightforward. When I have KES is my slope, if this KES slope is 0, what do you mean by that? That would be given by delta F is equal to L by R. So I would have a horizontal line. That's my neutral steer tendency of the vehicle, right? If this slope. So the slope, how does it come? For the curve, it is come. So what are the curve? So when I start plotting my first speed I enter, I take. So this variation is say it's from 0 means there is no speed. So as I enter, I would have my data going to be something like this. So first speed I'll have one value, second speed AY by G, like that it would be incrementing. And now I'm doing what a real vehicle test. So the vehicle is no more a mathematical model. It has got its all dimensions, operating state, suspension, everything. I'm just doing this test. So when I do this test, whatever the steering angle that is required as I increase the speed on this constant radius is what if I plot, that would go in this way. It will not increase ever like a straight line we have seen. And it would go to a point and then again it would fall like this. As you increase the speed and this lateral acceleration going to increase. So let me just connect all of them. Look at now. There is a point when the slope is 0. So this is the point, slope is 0, and here the slope is positive, and that keep decreasing and is 0, again negative slope that comes. So when the slope is 0, that's corresponding to neutral steer tendency of the vehicle. So when slope is 0, I would have my variation of lateral acceleration, steering angle for lateral acceleration, it's constant. So my vehicle is originally behaving for all the time neutral steer tendency. then irrespective of the speed at which I go with every lap, I would have the same steering angle required. That's what is the meaning of this horizontal line when this is. But the vehicle is behaving as an understeered vehicle, I would have this. So my acceleration would be corresponding to that would be this. And then you would have your oversteer tendency here. So this is going to be with oversteer tendency. This is going to be with an understeer tendency, I would say. Right. So when a negative slope means what? KES is negative. That refer to vehicle behavior is this. And in this equation, the KE is what you get at that particular lateral acceleration is negative. So this KES is not constant for a vehicle, that's varying. It can be greater than 0, 0 or less than 0, depending upon the operating condition, depending upon the non-linearity of the tire, depending upon the suspension characteristics, all the vehicle design and environmental factors that is accounted, and then the vehicle which is originally behaving as understeer vehicle can change into this. That's what will be witnessed, and such test is conducted for to predict the handling behavior, right? So what is the conclusion that you would say? The understeer behaving vehicle would change into an oversteer behavior vehicle under the higher lateral acceleration, right? So that's what you could say. So the next test is what is called a constant speed test. Constant speed test. Constant speed test, right? So in the constant speed test, what is that is there? You would go with the your test track is very broad and very larger area test track you are there, and you don't worry about though there is a lane marking for different radii of the path. You don't bother about it. So you go with constant speed, and you see that with the vehicle driven at a varying radii, right? So constant speed at various turning radius you would be doing it. So what I mean by that, you have first track, you go with the constant speed, you go on the next track with the constant, like that you would be varying your turning radii, and then you would work on the test and do the measurements, and those measurements would help you to look at the variation of steering angle required as function of lateral acceleration. Now again, AY by G. How is this going to be now? So again, let's look at for this test our governing equation L by R plus KUS into AY by G. So if I differentiate delta F with respect to now d AY by G, I'm just going to do some manipulation. This AY by G, I'm going to take out AY by G. I'm going to bring this effect also into the AY by G. If I take it out, and this is going to be what? LG by AY into R, AY into R plus KUS, right? So here I would be having it. I would be having this AY by G. If I do this, see, this is going to be. If I differentiate this, I would have, there's no AY here. So I take here AY by G out, and AY is U squared by R. So I would have this U squared by R, R goes. So this is, so this term AY, this term AY is what? AY is U squared by R. So if I substitute that here, RR goes, so LG by U squared. So I would have This differentiation comes to be Lg by u square plus KUS. Lg by u square plus KUS. So now I have this. So I have to have what a constant speed. So the speed is constant here brought in. So G is constant, 9.81 meter per second square. L is wheelbase of a vehicle, will not change. And the only parameter would change KUS is because of a real vehicle and a different operating condition. So if I differentiate this with respect to this, I would have this. So if I plot this now, I would have my vehicle. When AY by G is 0, there is no vehicle movement. So it starts from here, and I will have a line, and this line slope is what is going to be constant, and that is what is neutral steer tendency. When vehicle behavior is neutral steer behavior, K is 0, but I have this slope given by Lg by u square. So wheelbase into 9.81 by speed square. If I divide, I'll get some value. We plot that would sit in this straight line. And if this is straight line variation, that means steering angle to be increased as I go with this lateral acceleration increase. So lateral acceleration increases here is how I go with the constant speed, but of different radii I plot. So the test is conducted how it's a constant speed with different radii. So when I go with the different radii, that's where I have my lateral acceleration varies. And if I plot that, if it is of neutral steer vehicle, I'll have this variation. If it is, but it is not so, correct? It is not so. It is not going to be like that. So the variation would be how, if I plot, I would have something like this. I would have my points as this goes, something like this. And then it would be changing like this. So I would have like this. So if you see here, it's interesting, this there is a line parallel to this line. And that is the point, let's call point A. And this point is corresponding to, a neutral steer behavior of the vehicle. So till there, the vehicle behavior, when the slope is positive, what do you mean by that? I have this term plus IKUS. This entire thing is positive, right? See, when the slope is parallel to this, if this slope is positive and it is greater than this slope. So this slope and here the slope. Look at this slope. So this slope is greater than this slope. So the slope is gradually decreasing and the slope become equal to this line when that vehicle is neutral steer vehicle. That means what? The slope positive is because of the positive value of KUS added with this. Is what is ensuring that it is of understeer behavior. Something above this, it's of oversteer behavior, because after this point, the slope is negative, not negative, smaller than this. The slope here is smaller than this slope, and that means that can happen when KUS is negative. From this, it is subtracted. So that also, see here, that slope is going to be 0 here. When the slope is going to be 0, and that point is very important and critical point called B point. And you see till here it is stable, and this is an unstable state. So how this test is conducted? The vehicle enters with the constant speed on different radii test track, and every time the lateral acceleration and the corresponding steering angle is measured and that is plotted. And that variation is going to go with this way, non-linear way varying. Delta F is not linear like this. It's linear when it is only neutral steer vehicle where KUS is 0. But you have got your design KUS, and that slope when it is greater than this, that is understeer behavior. When the slope is smaller than this, that is oversteer behavior. And the slope is 0, whatever that I get here, and that corresponds to point B, and that speed, if you calculate corresponding to that, would be a critical speed or the critical lateral acceleration, beyond which your steering of your vehicle is lost. The steering control is lost. So you should write that. So when the slope is greater than neutral steer slope. Neutral steer slope. So this is what is neutral steer slope. The vehicle tendency is understeer. The slope is greater than, the slope is what I'm saying, this is slope. It's less than neutral steer slope. That's oversteer tendency of the vehicle. So the understeer tendency changes to oversteer tendency due to different operating condition and design aspects of your vehicle. You could say that, right? When the slope is zero, what do you mean by that? This entire thing is zero. That is Lg by u square plus kus is zero. And that says u is equal to under root of GL by minus KUS. So this is what is called a critical speed, which already we have seen. So this A to B is stable, controllable, but the behavior of the vehicle is oversteered behavior. By reducing the steering angle as your radii is changing, you would be able to have a control. But beyond B, it is uncontrollable, unstable state. And that speed corresponding is what is called a critical speed, and you can find out this way. So what are measured in this test? The delta and the lateral accelerations are measured. So on this plot is made. And then third test is what is called a simple test, and that's called a steer angle test, constant steer angle test. Right? So third test is constant steer angle test. Constant steer angle test means delta F I'm not going to change, it's constant. So when this is constant, then you may question, the earlier two plot we were plotting delta F versus lateral acceleration. But now I'm not going to plot that. Instead, I'm going to plot the variation of curvature as function of lateral acceleration. So this is what is the plot out of this test. What is there? Delta F is constant. That means it's fixed during the test. And what will be varied is the velocity is varied. The forward speed is varied for the test. So what is calculated is 1 by R is calculated. So 1 by R as function of lateral acceleration would be plotted. And you know now 1 by R is nothing but AY by U square. Because AY is U squared by R. So 1 by R is AY by U square. So if I measure AY, I would be able to have my curvature. That you divide by U square, you get the curvature. Right? So now, this test is very easy test to execute because both U is varied. When I say what I mean by that, you go first with the particular speed and then go with the next speed. You fix this and go sequentially, you are increasing this. So this test is simple test, right? And let us look at now how do you get this variation from this our equation. Delta F is equal to L by R plus KUS into AY by G, right? And to get now this, I divide this by L. So it's going to be delta F by L equals 1 by R. That's equal KUS AY by G into L. Now I have here 1 by R. Sorry, this is plus sign. This is plus sign. And here 1 by R would be 1 by R. Bring it on the side. It's delta F by L minus KUS into AY by GL. Right? So now I'm going to differentiate. I'm going to differentiate this with respect to AY by G. Why do I do that? Is because I get here my plot and I look at the slope. That's what. right? In every graph, I do that. So what is that variation I would get? So when my velocity is 0, that means it starts with some point. So you look at here, I decide my constant steering test, this steering angle, so much of radians, and this is my wheelbase. This would be there when I have my lateral acceleration 0. So I would have some point here, and that point value would be 1 by r is delta f by L. The curvature is delta f by L, and that would vary as I conduct this test in this fashion. So I just plot, you'd see that it goes like that, and then again it would increase like this. So how every time I have the same steering angle fixed, and then I go with the different speeds, and I look at what is my curvature, right? Variation. So I would have this. So if I connect this all nicely with a smooth curve like this, and you see there is a slope when it is 0. There is a horizontal line here. Slope is 0. So when slope is 0, so what is my slope here? D1 by R by, I have to take lateral acceleration as varying parameter, because this is delta f is fixed, L is fixed. So variable is AY by G. So AY by G, when I do, what is that I'll have here? So this is going to be 0. So minus KUS by L. KUS by L I have, right? KUS by L I have. So when KES is 0, the slope is 0. That means I will have a parallel line. KE is 0, the slope is 0. That's corresponding to that. But what is my curvature at that time? In this equation, let me substitute KE as 0. So I will have delta F by L. So that's this line. This is delta F by L for neutral steered vehicle, neutral steer tendency of the vehicle. If my vehicle is behaving originally neutral steered effect, then I would have my curvature fixed, and I have my steering angle fixed for irrespective of change in velocity. So any of the lateral acceleration, I will have fixed steering angle, and my constant take turning radius is not varying. That's what is neutral steer tendency. But now I have two slopes. One here is negative slope, and here positive slope. So when I take a negative slope, here it's going to be positive. KES is positive. So my vehicle from this side, whatever is there, is an understeer effect. And the slope here is positive. When I substitute here, it's negative. So KES value is negative. Then only I will have this positive slope. So after this lateral acceleration, the negative slope is very important, that vehicle do change originally, which is understeered, into an oversteered condition to come in. So such kind of observation of varying parameters, function of lateral acceleration, can be interpreted with any one of these tests. The OEMs are conducting test all these three tests, and to complement each other to have the same judgment. Or you can have one test and then you can have your handling behavior predicted. So if you are having study of an influence of non-linearity of a tire, what will you do? You take your tire and fixed in a vehicle and you do this test. And then you take your competitor tire fixed in your vehicle and do the test. And every time you change your tires, and then you are doing your test, you see that the variation in the handling behavior, how does it pronounce in your vehicle? That helps you to make a quantitative assessment of handling behavior of various vehicles on the test track. So these are the very popular test tracks to account and real-time behavior. Of course, we had looked at the steady state equation with the limitation of linear tire model and no suspension considered. Quite sufficient model for to develop some physical insight further. And we are going to continue our learning from the next class. Again, shifting back to our bicycle model and doing it. And this particular lecture I have to deliver to you to be keeping in mind, in reality, these are the behavior. Your KUS would be varying, not as a constant value in your vehicle. And we will also have one dedicated class, what all these parameter operating state of your vehicle are the design aspects of a vehicle that can change this KUS, and that change is momentary change. It's called a transient understate gradient. How are they come into picture is what we will separately look at in a separate lecture in coming classes. So with that note, I'll stop today's class. You have another 2-3 minutes to proceed for your lecture, next lecture. So I'll stop now recording. If you have any doubts, you can ask. Otherwise, I'll end now.